Okay, final clip from 3.4 here. We've gone to blue. I've made all 5 of these clips today, or going to have made all 5 of these clips, so I wanted to change too. So true blue here. Okay, this is on indirect truth tables. Here what we try to do is see if we can, understanding the operators. It's much more of a freehand and thinking thing, which, you know, some of the efficiencies of direct truth tables were like, but here even more so. We're trying to see if we can get all the premises true and the conclusion false. If we get it, we're all set. It's easy. We've shown the argument invalid. The tricky thing is this. If you you try to get the premises true and the conclusion false, and you don't, then you, well, gotta wonder, maybe you didn't do it well enough, or maybe you need to try again. And the question is, how many times do you need to try to show that an argument is valid? It's not, in the end, about the number of times. If you follow a certain principled method that I'm about to describe, then you'll know that it's valid or invalid. All right? And that method is this. You make truth value assignments when and where you are forced to, when it's the only way to get the premises true and the conclusion false. If there's no such thing at any point or points, then you have to consider the various alternatives that would accomplish what you're trying to do, either make a premise true or the conclusion false. Alright, so to the left, you might recognize this argument. We did it before. I picked the same one again so you can compare the methods. Looking at our first premise here, we have not P if and only if Q or R. If and only if, we think about when that's true and false, and there are 2 distinct ways to make an if and only if true. You can have the expressions both true or the expressions both false. So we don't have what I would call a forced option here. And if then, this is the main operator right here, as I'm pointing to, can be true. We can break it down into 2 options. Either the antecedent, the if part, is false, or the consequent, the then part, is true. We don't have either of those 2. We got T horseshoe F, we got the thing false. So we're going to need one of those 2. Negation, of course, is true when the expression being negated is false. And so for this third premise to be true, this is pretty simple, and clearly where we start, we need to assign R as false. And I write the true or false just below the letter or proposition that I'm assigning that truth value to. And the way then I write it over here is a big true to the right, reading across from the third premise saying that it is true. Now we have to assign truth values consistently. We can't talk out of both sides of our mouth here. So wherever R appears, we have to assign it false. And that's fixed based on the fact that we're getting this third premise true. Okay, now for the conclusion to be false, and we could have begun here because the only way for P or R to be false is if P and R are both false. Okay, so whether initially or now, we have to have P false for the conclusion to be false. But once I've made that assignment, I can make big false over here to the right. Now let's go ahead and assign P false wherever it appears in our problem. Again, being consistent. And now we're well on our way. In this case, we have all forced options. Let's look at the first premise first. The left side of the if and only if is going to be true, since P is false. We need the right side then to be true, so that we have true if and only if true to make. Once we have the left side of if and only if true, then the only way for the if and only if to be true is for the right side to be true. And the only way we can do that is to make Q true. Notice I got to understand the operators a lot better to be able to go through this process. But I have to. Once I got R and P false, I have to make Q true. I can go ahead and assign that wherever else it appears, which is one other instance. And at this point, it's all over but the shouting. You just calculate the truth value of the second premise. I wind up with if true, then true, which is true, because in parentheses I have true and not false, which is true and true. The parenthetical expression right here is true. The expression to the left, it doesn't matter once the consequent is true, but is incidentally true. So I have all true premise and a false conclusion. I've just shown this argument, therefore invalid, and I will report the same thing that I did before. Better be anyway, and it will always be if you do it right. I need to let P be true, excuse me, I wrote it right, P be false, comma, Q be true, and R, as is assigned in here, be false. All right. Expression to the right. This is a case that I chose because it has no forced option. Now, we're not looking for the same thing for the premises as we are for the conclusion, but in both, for the premises, there's more than one way for the if and only if to be true. For the conclusion, there's more than one way for an if and only if to be false. If we had an or in the conclusion like we did in the previous one, that would give us a forced option if it was the main operator. In a premise, something an and would fix options for us. Okay, so what I need to do is I need to break it into two options. Absolutely, either way we could go, or any way we could go. Excuse me, I should say, between premises 1, 2, and the conclusion. Conclusion's slightly simpler, so I'll go there. Okay, I need to make it false, so I can branch it into the left case where I let P be true and R be false. That's one way the conclusion can be false. And then in my other option here, I'm going to let P be false and R be true. P be false and R be true. Okay, I'm going ahead and quickly rewrite, and in the two distinct scenarios calculate and see if there's a way for the premises to be true and the conclusion false. Let me go ahead and rewrite both first. This one actually turns out valid, and if you think through what the meanings of the operators and definitions of the symbols are, I think it's interesting to see. Alright, in case 1 here, I have P true and R false. P is true, R is false. Okay. Now, this fixes my options, but I don't have a preference. There's no reason I need to go to the first premise or the second premise, but notice what happens in either case. Alright, first of all, let's note that the conclusion is false here. Alright, let's say I go to the first premise. I'm trying to make it true. Only way I can make it true once I have P true is to make Q false. Okay? So, I have to consistently assign Q as false, and what happens is here, as I picture in the book, we get a big fat X because I have true if and only if false. No other way I can go. All those assignments are made, and I just can't get, or don't get, there's no way to get that second premise true once I make the conclusion false, in this way anyway, and make the first premise true. Let's see what happens in the other case. It could go the same, it could go differently. Here I have P false, R true. It makes my conclusion false. Alright, so R is true, P is false. Alright, I'm going to stick with the same method. Again, I could go to the second premise, but I'll go to the first here. Now this time to make it true, I need to make the right expression, the expression to the right of the if and only if false, so I need to make Q true. It's the only way I can now make my first premise true based on the assignment of P is false. And this is the kind of thing you got to keep track of. It's a little trickier here. So now again, consistently assigning Q as true, I wind up with false if and only if true, which is not true, it's false. I can't do it that way either. And since, and this is sort of a matter of going through the process and seeing and talking out, not just what I've written, but what I've gone through in a particular order and thought about, that this argument is valid. There is no way. Okay, we have two options to make the conclusion false. Either way, we're not able to make both premises true and the conclusion false. So the argument's valid.